So this talk is, well, the abstract on the website was very grandiose, right, about Shannon and Hamming and the fusion of these two and trying to merge all of these different ideas. And we'll see how much of that we get through. Of course, our knowledge of even the Shannon world and the Hamming world is far from complete. So our knowledge of sort of a unified framework is even less so. But nonetheless, due to classical work in the 60s and 70s and more recent work, we are beginning to get some interesting insights. And that's what I'll try to share with you. Roughly speaking, the first 1.5 hours to 2 hours will be more general purpose background. And then maybe the last 2 hours will be more recent results over the last 10 years or thereabouts. Okay? Before I move on, I also did want to just poll the audience and just get a sense of what your background is. So firstly, how many people have taken a course in information theory, at least one course in information theory? Okay, good. So that sets a background. Just out of curiosity, how many people would consider themselves more of computer scientists than anything else? So a few computer scientists. Okay, good. Like just again out of just to get a sense, how many people have done at least 2 years of graduate school, like masters or a PhD or something? Okay, good. So that just helps me benchmark my level. All right. So to begin with, I really want to acknowledge acknowledge the people I've been working with, and credit goes to many of them for some of the newer results I'll be claiming. In particular, I'd like to highlight, so firstly, among the audience members here, Shashank Vatedka is a postdoc with me. He was a graduate from ISC. And Amit Alok is a recent graduate from IIT Bombay, is currently a postdoc with me. But also, like other people you may be seeing soon, Mayank Bakshi is currently a research faculty in Hong Kong, will hopefully be back in India relatively soon. And as always, credit to the students where due. Like Zithan Chen was an undergraduate, but he did some really remarkable work with me. He's now a postgraduate student at UMD. Eric Zhang is my PhD student. I'll be talking about some of his work, as with Thongshan Lee, who's currently a postgraduate student at Caltech. Nicholas Zhang is my student, as is Yehan Zhang. I'll be highlighting their specific works when we come to them. Swanand Kadhe, this got cut off, my mistake, but Swanand Kadhe is a student of Alex Princeton at Texas A&M, currently a postdoc, will be on the market soon. People look for jobs. I make sure that you guys know who to give credit for when they're coming and talking, right? Some of this really nice work is because of them. Of course, I really should highlight Bikash De, one of the co-organizers with whom I've had a very fruitful collaboration over the last like 10 years plus. Anand Sarvate at Rutgers, Mike Langberg, Carol Wong recently. So credit to you. The name of my research group at COHK, at the Institute of Network Coding at COHK, is Codes, Algorithms, Networks, Design and Optimization for Information Theory, which, as you can see, has been carefully chosen to be optimized for a nice acronym. So with that, let me finally take off my sweater and proceed with the talk. This joke is getting a bit old. I think it's time to move on to a different joke. But I figured, since I had the shirt with me, that I may as well try it one last time. But this really is the current logo for our group. My poor students complain every time I make them wear this shirt when they're giving conference talks and all of that. Next on the agenda is to come up with a group anthem. If you have some catchy tunes in mind or a dance, let me know. Okay? I love embarrassing my students. I'm getting to be a dad kind of guy. All right, so let's move on. So the context for this talk is, you know what? I'm just going to change slides with this. So the context for this talk is general adversarial channel, and let's spend the next hour just getting to know these characters and their properties and their capabilities and so on reasonably well. So there are three primary players. There's Alice, the encoder. She has a message and she can encode that in a certain manner into a transmission X. Okay. Oh, thank you. Thanks. There's a channel. You know what? I really do like standing close to here, so maybe I'll just use this. There's a channel into which a jammer, whom we'll call James because he's a jammer, will be jamming information. So this jammer could be, it could be random noise, but it could be adversarial noise. It could be noise that depends on the actual transmission in possibly a worst case manner, in a manner chosen so as to try to make communication as difficult as possible. So he'll do that to the channel. And then the decoder, Bob, the minion over here, Bob the decoder is going to get an output which will be some function of the two inputs of the transmitted code word and the channel state, right? So think of the state as like noise. Noise may be being added to the channel or being multiplied with the channel or something, but nonetheless some state. So these are the two inputs to the channel, and then there's the output of this channel which comes out. Okay. And the goal is to communicate a large message, to communicate many bits of a message reliably over the receiver, over this noisy channel. Now, yeah. So this is just what I've already said. So okay, just to highlight, when I say message, that will be the input to the encoder. When I say code word, that will be the output of the code of the encoder. And the reason I distinguish between these two is because sometimes it's not a deterministic mapping. Sometimes for the same message, there may be multiple code words that could be transmitted. So implicitly, and we'll make it explicit later, but implicitly there could be randomness in this encoder. Okay, randomness of different types, maybe correlated randomness, maybe independent randomness, or things like that. But nonetheless, there could be randomness. So we'll distinguish between these two. When I say a noisy code word or a received code word, that's what's happening over here. State is something like the noise, right? So that's what this is. And the message estimate or the decoded message, that's what Bob is getting. Okay. We'll talk again about what it means to be reliable, what the relationship between M and M hat. But just to get first few terms out of the way, that's what's going on. A little bit more formally. Now, again, actually, there are many different problems we'll try to put under this umbrella. So we'll have to even further specialize this. But to get some more notation out of the way, so first of all, there's the block length, right? That's the number of channel uses. That will typically be n in our thing. So this channel gets to be used n times. Alice will typically have a message with nr bits, right? We'll usually restrict ourselves to bits. Again, we could have different alphabets, but whatever. Her code word X will be an n-length sequence over some alphabet, often binary sequences. In fact, for much of this talk, I'll focus on either the binary erasure channel or something like the binary erasure channel, something like the bit flip channel, or things like that. But in general, it could be an arbitrary alphabet. It could even be a continuous alphabet. It could be like some vector from Rn, for example, right? Things like that. And her encoder will be called gamma. James generates his jamming state S in Sn using the jammer lambda. So this lambda is going to be a function. Now, there'll actually be many different problems in this framework. So sometimes this jamming function will depend explicitly on X. Sometimes it will depend on some function of X, with certain restrictions on it. So we'll again have to go in and specialize this more as we look at specific problem settings. But generally speaking, there'll be some sort of dependence of the output of this jammer to this X over here, generally speaking. Okay. There will usually be an explicit dependence on the encoding function. So the jammer will usually be allowed to know the specific code book, the specific coding strategy, the specific function that Alice uses to map from M to X. Okay, and that's really why this is adversarial, right? The adversary knows knows how you speak, your speech patterns, and tries to generate some jamming pattern that tries to confuse the decoder on the basis of the speech pattern. And as a simple example to keep in your mind, like maybe this channel is something like an additive channel. Maybe what comes out of this channel is a sum of this and this. And in this case, one sort of jamming strategy that the adversary could use would just be to transmit another code word, right? And therefore, what would come out would be the sum of two code words, and the decoder would not know what was being transmitted. right? So that's an example of something that the adversary could do, which would be very different from a random noise channel. The probability that a random noise channel would generate a code word, would generate noise that looks like a code word is small, right? So, but in an adversarial setting, this is possible, right? All right. So, so that's the jamming state. Now, the channel, and now again, keep in mind that we are distinguishing between the channel and the jammer. So the channel generates the noisy code word by in a deterministic manner and a memoryless symbol by symbol manner. So for example, even though the state could be chosen in a complicated way depending on x and so on, once a state is chosen, then the y will be always a deterministic function of the x sequence and the s sequence, and also a very simple memoryless symbol by symbol deterministic function. Okay. Now this seems like a massive restriction. It's not that bad actually. It can be argued that, see slide blah later. Okay, so I clearly never got around to that. This is what happens when a 4-hour tutorial is put right at the ISIT deadline. So I apologize. Okay. But basically, one can argue that even if you allowed yourself, for example, for y to be a probabilistic function of x and s, that can be treated, you can just sort of expand your state space and so on, you can deal with that, right? Or things get more complicated if you don't allow memorylessness, but this is already a very rich class. For example, it encompasses many of the classical adversarial problems we think about, where Alice has a transmission, let's say a transmitted binary vector, James gets to add a binary vector of a certain Hamming weight, okay? And then the output is a sum of those two. So the sum function, the function where yi is equal to xi xor si, that's a pretty simple function. But the underlying complication comes from the fact that si itself is a complicated function, right? Now I know that for some people in the audience, they are indeed looking at, like for example, I had a nice conversation with Vinod this morning, where he's explicitly interested in channels with memory and so on, and that unfortunately we cannot capture with this model, right? There are problems with that. I know Marco has done some excellent work in somewhere along those directions, and that might be worth looking at. All right. So then Bob gets this, and then he tries to estimate the message m that Alice was trying to transmit. He outputs an estimate m hat, and hopefully this m hat is kind of like, and we'll discuss what it means for m hat to be like m. So maybe you demand it always to equal that. You demand that m hat is always equal to m. Maybe you demand that m hat is equal to m with high probability, or you have an average or maximum probability of error. And again, we'll get to all of those later, right? But there could be different notions in which m hat should equal m. Okay? And the code is just the encoder-decoder pair. Sometimes we'll abuse notation. By the code, we'll just say it's a collection of possible code words, like if it's a deterministic code or if it's a structured random code, sometimes we'll just focus on the collection of x's. But generally speaking, the code is both the encoder-decoder pair. Okay? That may be, yeah, okay, that was another thing. Yeah, you're right. The encoder is, here is psi, here is gamma, and things change in the middle. I'm sorry. Yes? So capital W for this talk will be a deterministic function. So just as an example to keep in mind, here are two examples of W. So, think of an adversarial binary symmetric channel W, or adversarial, let's call it a bit flip W. So in this case, W of yi given xi comma si would be equal to yi. So in this case, the yi would be equal to xi plus si. Okay, actually I can just write it like this. Okay. In general, this W of yi given xi is a probability distribution. In this case, the probability distribution has probability 1 of happening like this and 0 otherwise. In this specific case, when the probability distribution is a delta function, then yes, you're taking a product of zeros, and the overall probability distribution will still be a delta function type probability distribution. In general, you could have stochastic process, but again, there are arguments that can be made that you can expand the state space and get close to the original problem over there. Okay, it's a technicality which I won't get into. Good. Any other questions about the basic setting? For much of the talk, okay. So there are results that we can give for infinite alphabets, and I'll explicitly point those out in places. Infinite alphabets of the kind like L2 restricted or so on. But in some cases, things become subtle, and I will be a bit sloppy, and in some cases, I will not point that out. So if there are specific models where those are of interest, please revisit this question and ask me. Okay. Yes. Any other questions? Okay. All right. Good. By the way, I really genuinely do like questions and feedback. In fact, one of the models being discussed over here is to do with feedback. It's kind of challenging to do in a Hong Kong context, like especially because I have an accent, Indian accent. They don't understand me, and it's the authority figure relationship, professor student. So I once gave a 2-hour lecture like this. And I was just waiting. Okay, who's going to be the first student to raise his hands and ask a question? Never happened. Like I swear, they paid more attention to me than ever before or after, but nobody ever asked the question. Yeah. So I just wanted to pause and take note of the fact that I really do appreciate questions, and keep them coming. All right. So moving on. Now things that will be important will be things like. So Alice's encoding function. So it takes as an input this and a view. So in this case, Alice's view will typically be just a message, right? She takes a message, and potentially with some private and with her view, she then generates the output, right? Now, but in some settings, like the view could be more general. For example, we will consider, as one of the examples of this model, we'll consider models with feedback. So Alice gets to see either the full output of the channel, symbol by symbol, or she gets to see some function of that output of that channel, symbol by symbol, right? So this view could encompass actually a sequence of, so it's actually more complicated, and I'm simplifying it here. But there could be a sequence of views, and then her encoding function could depend on the message and the channel output so far, right? So that's one possible output. In some problems, like for example, for those of you who've heard of this, the Gelfand-Pinsker problem, Alice's encoder could depend on the noise as well. So it's sort of the reverse thing, where there's an adversary who's generating noise, but Alice gets to see the noise, right? And this happens in, for example, like let's say you have a CD, right? And you want to write on the CD. And the CD is dirty. It has some noise on it. So the encoder, the person writing on the CD, knows where the noise is and wants to figure out how to write on this in a manner that's understandable, right? So this is the so-called Gelfand-Pinsker problem. And here, so the encoder gets to see this and therefore tries to encode in a certain manner like that, right? So in general, you can absorb many of those things into Alice's view. And Alice's encoder may also have encoder constraints. Now, for example, one of the questions was on, like, do we allow infinite alphabets? And often in infinite alphabet cases, Alice is transmitting a sequence of real numbers, but with a power constraint. So summation of her xi square in that case may be bounded by a quantity that's linear in n, right? So in that case, then there would be some encoder constraint over there. And sometimes we will explicitly enforce these as well, okay? So again, just to highlight, Alice's encoder will depend certainly on her message, potentially on other things called the view, which may become non-trivial in certain problems, for example, feedback. And there may be constraints, like, for example, power constraints. Yes? So channels with state, it depends on how you use that terminology. So for example, you could say that, I mean, this what I'm describing over here is the arbitrary varying channel, and in principle ABCs include that. Channel with state could also include somehow Markov channels where the channel evolves as a function of time. That is not included here because we want independence between the WIs, right? So it sort of depends on which particular part of the literature you're talking about, because that term may have different meaning for different things. Yes. Any other questions? All right. Okay, so similarly, James's jamming function will, so it will depend on things. So it will depend on James's view. This could be the code word, it could be other things, but it also always includes the code. I just want to re-emphasize this. It always includes what Alice's encoding function is, and may also include some other quantities, which we'll look at examples later, and we'll look at specific problems later. Okay. And again, there may be jammer constraints. So the jammer may have power constraints and may not be able to put too much in the channel. Okay. Bob's decoding function. So again, depends on Bob's view, which will typically be the channel output, potentially other things, and has to output the message. Right. Okay. Yeah. Again, we'll delve into specific examples later. So this is just a recap, everything that we've talked about so far. It's really just notation you've already seen before. One last reminder, message M, transmitted code word X, received code word, noisy code word Y, channel WY given X comma S, state as S, and then there are various views. There's the decoder, it outputs M hat, and Alice, Bob, and James, right? Okay.
Simply a restriction on the number of possible code words or jamming code words or whatever.
Is what all?
Is it essentially a restriction on the?
Is what essentially a restriction? So the view is a restriction on the inputs. The restriction on the number of jamming vectors would be a restriction on the outputs. So that would be a constraint, right? So think of the view as being characterizing what are the inputs to the jammer or to the encoder or to the decoder, whereas the encoder constraints and the state constraints would be restrictions on what types of actions they can perform. Yeah, so this is all very abstract. So I think we're going to dive straight into slightly more specific examples, which will be a little bit more concrete, and then even more specific examples with particular channels. Okay, but let's dive into a specific example, okay, we'll do it step by step. So this first hour is really just going to be basics, right? So so firstly, the results depend on the encoder state and the decoder, and so let's look at the encoder first. So think of this really like a table, okay? So if you're trying to classify the types of arbitrary varying channels, types of jamming problems, here are some of the types of interesting problems you may be interested in. There are others, by no means is this comprehensive. I'm listing things here that we know some things about, some non-trivial things about. So there could be input constraints, and this is a little bit misleading. I don't actually like the name input constraints. It's called input constraints because these constraints are on the input to the channel. Okay, so when we say input constraints in the literature, in the AVC literature, in the arbitrary varying channel literature, input constraints refers to constraints on X. So those are the inputs to the channel. They're actually the output of the encoder, right? I would actually call them code word constraints, but nonetheless. So and for example, there may be a power constraint here, or there may be other things here. Okay, and we'll talk about this a little bit more. There could be restrictions on the types of input functions. We'll again see that on the types of feedback, awareness of state, and computational constraints, and so on. And we'll see examples of each of these in the next slide. So I'm going to jump straight into that. So, for example, it could be that there's a function, there's a cost constraint function on the inputs. So every code word has a certain cost. So for example, it could be that if your code words are binary vectors, then the cost of a code word is the number of ones in the code word, okay? And you're not allowed to have any code word with cost higher than, let's say, rho. So therefore, you're restricting yourself to code words of weight at most rho. That's one example. You could have restrictions on the L2 norm of vectors or other such constraints, right? So that's an input constraint. It could be an average constraint, it could be a maximum constraint. These have implications, different, like for different problems, different sorts of results are obtainable under different types of constraints. Okay, so I'm just going to be explicit about these. Okay, different types of encoding functions, and this really is important. This has direct implications in the types of capacity results you can prove. So you could have deterministic encoding functions. These are typically the ones we think about. So in a typical information theory class, coding theory class, we tend to think of an encoder or a code as really a mapping, a deterministic mapping between the message that Alice wants to transmit and the transmission she'll actually have, right? So maybe it's you take your binary vector of inputs and then multiply it with a matrix, and then you get a code word. Often we think of it that way, right? But there could be flexibility. So it could be that the encoder uses one of two different types of randomness that I'll expound on later. And in different problems, these have differing capacities. So one really has to be careful. So deterministic is clear, right? So you have a deterministic function. A stochastic encoder is allowed to use some private randomness over here, so known only to the encoder and to nobody else. Okay, and even just allowing yourself to use some private randomness can sometimes drastically increase the capacity or make the problem easier or whatever. Okay, so easier code design and so on. So that's stochastic encoding, and then we have randomized encoding. So in the literature, and I understand that this is a little bit confusing in terms of terminology, because random, stochastic, at least in English, even in math, we tend to use them interchangeably. But in the ABC literature, these two things have different meanings. Randomized encoding specifically refers to the scenario where the encoder and the decoder share common randomness that is unknown to, that is independent of the adversary. So the state is independent of this common randomness over here. Okay, so or at least the input to the jammer is independent of that. So let's very quickly revisit all of these things. Somehow the simplest thing that the encoder could do is have a deterministic mapping between inputs and outputs. It could have probabilistic mappings between the inputs and the outputs using private randomness, or it could have probabilistic mappings using common randomness. Now, as you can imagine, yes?
Think of the randomized as a special case of the stochastic.
Yes. So anything that you can do in this, so yeah. So if you can implement a deterministic, so if you have common randomness, you can certainly implement deterministic encoding, right? You can also implement stochastic encoding, right? You could just sort of separately generate whatever. So doing this requires more and more resources, and therefore predictably, you can show without too much effort that any capacity that you can achieve via this, you can achieve via this. Any capacity that or any rate that you can achieve via this, you can achieve via this. Any rate you can achieve via this, you can achieve via this. Okay? And so from an achievability perspective, from a code design perspective, these different types of encodings require more and more resources, but they come with potentially, not always, but potentially higher and higher achievable rates. Okay? From an impossibility perspective, it goes the other way around, right? From an impossibility perspective, if you can prove that the rate is no larger than something for this, then that puts an upper bound on the rate over here, and it puts an upper bound on the rate over here, right? So usually, if at all possible, we'll try to prove our achievabilities for deterministic codes, and we'll try to prove our converses for randomized codes. Okay? And if these two happen to match, then we really have characterized like the spectrum, right? So we won't always be able to do it, and indeed in some cases these capacities will indeed be different, but that will be our goal. We will try to prove achievabilities for deterministic. We'll try to prove, well, here it becomes a matter of taste. I'm usually agnostic to the difference between deterministic and stochastic encoding from an achievability perspective, right? Because tossing a few coins is not too much of a burden on an encoder, right? So from an achievability perspective, I'm fine with either deterministic or stochastic encoding. From a converse perspective, however, it really is important to try to get a converse for like at least stochastic encoding, because there are specific cases that I'll try to highlight where the capacities are different between stochastic encoding and deterministic encoding. Okay? So that's a little bit important. And indeed, in some cases, like one needs to go a little bit beyond the typical information theoretic methods to parse out the difference between these two. Any questions? Yes? Well, not explicitly, or not explicitly in the models I'm considering. Sure, you can always define a model in that way. Let's see. Usually, I mean, I would say this, right? So usually if there's some sort of key which is where you can make an argument that that there is h of k given k prime. Let's say the jammer has some random variable k prime which is correlated with k. So if there's h of k prime given k which is non-zero, then you can use the hashing lemma and argue that you can generate a key which is independent of the jammer's view, right? On the other hand, if k prime is equal to k, if you can really estimate whatever, then you may as well just assume it's part of code design, right? So I would argue that it's not maybe the most interesting model over there, right? Though with a pinch of salt, like if you truly care about the number of bits of common randomness, which again in some models we'll care about, because it's a very strong resource to have common randomness between the encoder and decoder, then then I'm not entirely clear on what one can do over there. Okay. Good. Other questions? All right. So moving on. Okay. So now encoder characteristics. You could have feedback, right? So the encoder could see symbols being transmitted, like what Bob the decoder is receiving symbol by symbol, and there could be different types of feedback as well. There could be no feedback. There could be full feedback, so the decoder gets to see everything that this is seeing. Could see noisy feedback, so there could be some noise in the feedback link as well. There could be partial or rate limited feedback, so maybe after every 10 symbols forward, the decoder is allowed to send 1 symbol back, right? Something like that, so partial feedback. So there are many different models. Again, I'm trying to be very general here. The underlying motivation for this talk is Bikash, I, and a few others are trying to write together a monograph, pulling together the much of the literature in this. So we're trying to, in a single framework, combine many different models. So much is indeed known about some of these models, or I should say it the other way around. Some things are known about many of these models, but a full characterization is still far away, right? But these are certainly some of the types of different models that have been investigated. Okay. All right. Yeah. So again, you can have no feedback, full feedback, partial feedback, noisy feedback, and so on. So I'm not going to parse the details here. I think it's sort of understandable what they are. Awareness of state. So we talked a little bit about this Gelfand-Pinsker type problems. So there's a jammer, like someone gets to decide how to scratch your CD. Now on the scratchy CD, you want to store some data. Well, scratchy USB nowadays, I guess, you get to decide how to store your data, so that the decoder can then still reconstruct it, because the decoder doesn't know which parts were scratched before before the encoder got to it, right? Because a scratch looks like a scratch looks like encoding, can't necessarily distinguish between these. So so that could be like a state aware encoder. And again, there are different ways you could parse this. So maybe there's no view, maybe there's a non-causal view. So maybe the encoder gets to see the whole USB stick before it gets to encode. Maybe it can only see it causally, so it gets to see like maybe the disk is spinning and it gets to see the thing and then decide whether to write on it or not. Maybe it gets to see a noisy view. So there are different versions of these things as well, and so on. And again, I'm not going to parse the specific technical details here. Okay. Yeah, nature of the state knowledge. Okay. Some really interesting recent work says, well, okay, so we're thinking of this guy as an adversary, and that's good, right? We want our capacity results to be robust to different types of noise perturbations. We always think it's an AWGN channel or a BSC channel or something, but maybe it's not quite that smooth, right? Maybe there are some perturbations. So what if the adversary is, so what we treat it like an adversary, but put reasonable restriction on adversary, right? So in nature does not really do exponential time computation. So maybe it does polynomial time computation. So under this restriction, what can you say? And there's been some really interesting recent work in this direction, which actually I probably will not have time to get to, but I can point you to the literature if you're interested. Okay, so all of that was encoder characteristics, right? Encoder restrictions. The jammer restrictions will be similar in nature, but I'll highlight the differences where they exist. So there could be power constraints on the jammer. So again, those are sort of like in the literature, these are called state constraints. So there's a constraint on the types of vectors that the channel can, that the jammer can introduce into the channel. Again, there could be average or maximum, and again, this makes a difference to the capacity characterizations. There could be, let's see, input jamming functions. Yeah, so this is going to be one of the major themes of today's talk. So there could be causality constraints. So, and there are different types of causality constraints. So think of the jammer has to decide how to choose a jamming function, how to choose a state, how to choose a noisy state vector to impose on the channel. Now, typically in coding theory, we say, well, you know, if the adversary can flip at most p fraction of bits, then what is the worst case thing, right? But this often pre-assumes that the jammer gets to see the full transmission before deciding his jamming vector, right? But often, this is too strong. Like often, maybe he's only getting to see things in a structured manner. Maybe he's getting to see things in a manner indexed by time. So at one extreme, he could be oblivious. He doesn't really get to see what is being transmitted at all. That could be oblivious. It could be causal. He could be seeing things symbol by symbol and then deciding how to jam, right? But it could be delayed. It could be delayed by a certain number of bits. It could be delayed by even a single bit. It could be look ahead. It could be omniscient. And I'll talk about myopic specifically later. That will be another theme for today's thing. So we'll talk about each of these things. But really, maybe the jammer does not have full knowledge of the X when it's deciding a particular symbol SI, right? That's the theme of this type of constraint. And we'll just parse into a few of the, we'll dive into a few of these right now, because those will be things that will take up the last 2 hours of today's tutorial. Okay. So, so let's see. So oblivious could be things like the sequences can be anything that match the state constraints, and they can depend on the code, but they're required to be independent of the actual transmission. Okay, so to think of a scenario like maybe the jammer jams has a single antenna, and this antenna can be used either to receive or to transmit. But if he's trying to jam, he can't listen. Okay. So he knows that if the transmitter, maybe Alice is a spy who's transmitting to her home base, so Alice would use this transmission strategy, but when she's actually transmitting, the jammer, just because he's trying to jam, can't actually listen to what's being transmitted, right? So in this case, the sequences have to be oblivious to the actual transmission X, okay? Oh, and just to remark over here, sometimes because of this, the stochasticity is quite important. Like what you can do with private randomness is quite important. Delayed. Now, okay, so maybe the adversary can do what he wants, but he has to have a certain delay. He can't his jamming vector S. So when he's choosing his so when he's choosing his tth symbol, the tth symbol can only be a function of the t minus dth channel input, okay? Because it just takes a certain amount of time for him to do some processing, and then the channel output can only be restricted by that one. It turns out even a little bit of delay, in fact, in an extreme example, I'll show a certain channel model where we can show that the capacity with no delay and the capacity with a single bit of delay is drastically different, okay? So delays can have a drastic impact on the channel capacity. And strictly causal is basically the model where there's a single bit of delay. So that's what I mean by a single bit of delay can have a big impact. Instantaneous. So yeah, Arya's not in the audience, but he has worked where maybe the jammer is truly a jammer, but it has to decide how to jam on a symbol by symbol basis. It has to decide what function to use, but it has no memory. It's like a amnesiac jammer. Okay, and there's been some nice work in that direction. Exactly causal, so I'll focus on some recent work characterizing that. There's some look ahead, so he even gets to look ahead before jamming a little bit. And potentially surprisingly, just to foreshadow the results a little bit, at least in some of the models we can characterize, it turns out that these capacities are really quite close. Whereas notice I just said that even a single bit of delay can change the capacity, right? So there's some inherent asymmetry in time. Like it seems critical to know the current bit, but it's not quite so important to know the next few bits even. Okay, so that will be sort of an interesting theme that will come out in this. And then the next one is truly hard. Like if the adversary knows everything. Oh yes. Loudly. Yes. So in everything, so whenever we are talking about an adversarial channel, the adversary will always have access to the codebook. And by the codebook, I mean the following: the function that maps the messages to the code words. Okay. And notice I'm distinguishing between this because for the same message, there may be multiple code words. In fact, there may be multiple code words with different probabilities. It could be the case that one message gets encoded to a code word with some probability, a different code word, a different probability. The same code word may be an encoding of multiple different messages with multiple probabilities. All of these can happen. And indeed, there are problems where we can actually show that weird code books like this can actually outperform deterministic or even sort of uniform stochastic code books. Okay? He always knows these mappings, but he does not know which mapping instantiates. So he does not necessarily, in the oblivious setting, he does not necessarily know the X that is being transmitted. But for example, in the causal setting, he would know the mapping, and he would also know the xi or xt when he is deciding st. But he doesn't necessarily know the future. Okay, so I mean these are sort of delicate definitions. And when we revisit this in the last 2 hours of today's tutorial, we'll actually do sort of very explicit examples for very explicit channels. You'll get to see this again. Okay. Yes. Any other questions before I dive into this? Okay. All right. Yeah. So the omniscient problem is actually what I would call the Hamming problem, right? So this was between Shannon and Hamming, and really the omniscient problem is the Hamming problem, or at least what I would like to call the Hamming problem, where the adversary gets to see the full transmission, knows the code book, there's nothing hidden from the adversary, and decides like a maximally worst case jamming thing. And this is truly hard. The capacities for many of these types of problems have been open for a long time. And in my mind at least, this is really one of the more interesting and important problems, and many of these are approximations to this truly hard problem, so we're trying to get in that direction. Okay. Yeah, there are also geometric implications of these. Finally, one type of problem I find quite interesting, over which I've worked quite a lot recently and which we've had some interesting progress, are myopic channels, where the jammer gets to see a noisy version of what the transmitter is transmitting. Okay? So instead of seeing the transmission X exactly, well, when in reality are things ever perfect, right? There's always noise. And maybe there's benign random noise, like some channel, some discrete memoryless channel perhaps, or something like that, going from Alice's transmission to James. And this view could be non-causal, it could be causal, and so on. But we'll look at models like this. And this also has some interesting results. Okay. Yeah, again, types of computational constraints, types of decoder characteristics. So let's see. So I have 15 more minutes roughly until the first break, right? Okay. So one type of thing that will be kind of important will be the type of probability of error criterion. So maximal probability of error or average probability of error, right? So by maximal probability of error, we will typically demand, and again we'll formalize this on the next slide or two, but maximal probability of error will be for every message the probability over the other types of randomness, and we'll make that more explicit, but over the other types of randomness should be no more than something than this quantity, okay? And you want that quantity to go to 0. What are the other sources of probability? Well, potential randomness over here in the jammer actions. Potential randomness, for example, if there's any noise in the jammer's view. Potential randomness in the fact that the encoder may be using some private randomness. Potential randomness in the common randomness, right? So there are many other potential sources of randomness. But for the maximal probability of error, we'll demand that for every message, the decoder gets that message correctly with high probability. Okay? Whereas the average probability of error will typically be, you'll allow yourself to average over the messages as well, and for some fraction of the messages, that will be allowed to go to 0. Okay? So those are the two types of error criterion we'll often focus on. Sometimes we'll demand that the probability of error be indeed exactly 0, and indeed in some cases this will turn out to be not really different from the maximum probability of error. Again, we'll see this a little bit more carefully. Okay? All right. Yes, so I noticed that as well. This is another symptom of the ISIT deadline. So Amit, Alok, Jayant Budkule, a proud graduate of IIT Bombay, helped me a lot with these slides. Credit to him. I really should be explicit. Shashank, Amit Alok, my student Nicholas, Yihan, like people I've worked with have contributed enormously to these slides. I'm standing on all of their shoulders, and I'm very sleepy, so I'm just powering my way through this because of their tremendous work. They certainly do. I hope they're getting some sleep. While the cat is away, the mice really should be playing. So, well, Shashank can't, he's here. All right. So, maximum probability of error metric, average probability of error metric. Yeah, you know, these things have different sources of randomness depending on the different problem. So I'm really going to sort of hide that in the statement. And again, when we come to specific problems, let's say a myopic channel or something, then we can be more explicit about the sources of randomness in these definitions. Okay. All right. All right. Types of decoding functions. So there could be a deterministic decoding function, there could be a stochastic decoding function, there could be a randomized decoding function, right? By now you should, you know, these should all look familiar. It turns out one of the classical results in the ABC literature, and in fact many of these classical results in the ABC literature are basically exercises on the back of a chapter of Cesare Narayanan, right? But one of these classical exercises basically shows that for many, if not most, there are certain versions where it's still not clear, but for most of these, actually, the decoder may as well be deterministic. Whenever the decoder could try to do some stochastic or something random, usually you can use an averaging argument and say, well, the decoder may as well be deterministic. Okay, I say this usually, but not always. There are specific problems where we conjecture a gap, but it's not clear right now. Okay, so but we'll just leave it there. Okay. All right. Let me take that back. Let me take that back. Randomize is quite different. So usually, whenever you can do something stochastic, you can do deterministic. Randomize is an entirely different beast. Randomized says that the encoder and the decoder are allowed to have a common key that the jammer doesn't know, and this is quite powerful, right? Imagine that if, I don't know, you share a password, a key, like it's like having a password, right? If you have a password, you can use it to verify, you can use it to do various things. So randomize is indeed truly different, and we can show differences between these, but the first two often are. Okay, again, the decoder could be aware of state and blah, blah, blah. You get to, this is similar to stuff you've seen before, so I'm not going to torture you with these again, and we'll move on. Okay, decoder awareness of state. He could see. So maybe the decoder knows what the jammer has been doing, though the encoder doesn't know. And again, you can say some things. Okay. All right. So we have 10 minutes, and in these 10 minutes, I'll try to review what almost everyone has taken an information theory course. So I'll try to just review this very general setting in one sort of basic benchmark channel that people have seen before, right? So hopefully this is all sort of known stuff. There may be a couple of little things here that might be of interest to you, but it'll at least get you used to the notation and so on. Okay. So here the Shannon view is stochastic channels. The noise S is just random. It's like S is chosen according to some probability distribution, and then you try to compute the capacity. You try to compute how much communication can be communicated. Again, you can have an average or a maximum probability of error metric, which again have reasonably clear meaning, so I'm not going to go into that. So The channel capacity is the maximum rate achievable as you take a sequence of codes, and so the supremum over all rates that are achievable under either the maximum or average probability of error metric, which they turn out to be equivalent. It doesn't matter if you take an average or maximum probability of error metric, but in both of these metrics, the maximum rate is tight. In terms of achievability, we try to show the existence of a capacity achieving code. So Shannon's strategy was to choose an ensemble of codes with the optimizing probability distribution, and that'll achieve the sort of Shannon limit, the mutual information limit. A subsidiary goal over which coding theorists have made considerable progress over the last, well, especially over the last, let's say 20 years, but or even the last 10 years, has been computationally efficient codes, which basically get to the Shannon limit, right? So we really know quite a lot about the achievability. The converses are also impossibility results, which are really quite tight. In fact, there's a lot of work, including by people in the audience, on even figuring out the second order terms, like how close you can get to these fundamental limits, how quickly, non-asymptotically in n, and so on, right? Okay, so for the expository purposes of this tutorial, since we'll be focusing on adversarial channels, I wanted to just get us comfortable with the erasure channel, right? It's a very simple channel, as Rudy likes to say, in turn quoting other well-known people. But everything we learned about coding theory, we learned from the erasure channel, right? So everything, well, not everything, but many of the things we learn about AVCs, about arbitrary varying channels, about the Shannon Hamming view, the shamming view will be via the lens of the erasure channel. Okay, and the erasure channel, you can, in this view, in this W view, you can view it as the channel input is binary, the channel output is 0, 1, and this erasure symbol, and yi is equal to xi when oh, this is a typo, when si is not lambda. So basically, when the state is when the state vector is not like this. Okay, this is incomplete. I really should write it like this. So so in the erasure channel, let's say the adversarial erasure channel, you can have S is in the S, fancy S to the n, which is 0, 1 to the n, and then W of y given x comma s will be yi is equal to xi if si is 0, and lambda if si is 1, right? So again, just to get us used to this notation, this is one way to write the adversarial erasure channel as a ABC, right? And this is basically so let's say you get a vector like this. This is a little bit too small to read, but you can imagine what's over here, right? The sequence of zeros, ones, and erasures. This is what you receive, and we'll say code words are compatible if their unerased locations match what you observe over here, right? So that's compatibility. So I'm just defining compatibility because it's related to, but slightly different from, the Hamming distance between binary vectors, right? And since I want to focus on the erasure channel, so instead of talking about the Hamming distance between pairs of vectors, I'll focus on compatibility. Is this code word compatible with this observed vector? Okay, so that's what compatibility is. Okay, and here's a geometric view between average probability of error and maximum probability of error. So maximum probability of error would say that, okay, mentally when we think of coding theory, we tend to think of Hamming balls, right? So that's why I've drawn this picture over here. This picture, a bipartite graph, will actually be more useful for erasure channels. Okay, so I'll draw your attention to this later. But really, a maximum probability of error metric is like saying that for most y's that could result, so think of these black dots as potential transmitted code words. Okay, so for most potential transmitted code words, most of the received code words will be somewhere in this ball. For this transmitted code word, most of the received code words will be this ball, and so on, right? So for a maximum probability of error metric, geometrically what's happening is that for most of them, most of the received code words, there'll be really only one sort of typical likely transmitted code word. There could be a few, like in this intersection, where there are two or more, right? But that's a small fraction of the volume, right? Geometrically, this is roughly what a maximum probability of error metric is saying. An average probability of error metric would say, well, for many balls, for a large fraction of the balls, this is still true. But for a small fraction of the balls, there's significant overlap. And if you happen to fall in this region, then you're kind of in trouble, right? So so this would be still a good code under an average probability of error metric if the number of such heavily overlapping balls is small. This would be under a maximum probability of error metric, right? For the purposes of the erasure channel, what will be more important will be, so you're transmitting binary code words, you're getting ternary vectors, right? Zeros, ones, and lambdas. And under a maximum probability of error metric, there should be relatively few confusability y's, right? This y is confusable with two different x's, right? But most of the y's are not really confusable. So that's the analog of this, and this would be sort of the analog of this one. Only a small fraction of the y's hopefully are confusable with many different x's. Okay. All right. Yeah, geometry, for all of us really gives a lot of intuition, and these will be the objects we'll be using to discuss things for the rest of this tutorial. Formally, you can write the probability of error statements and so on. And as I've said earlier, we'll try to prove achievabilities under a maximum probability of error criterion, and if possible with deterministic codes, sometimes not, sometimes with stochastic codes. We'll try to prove converses under an average probability of error metric, and if possible with randomized codes or at least stochastic encoders. If not, then with maximum with other things, right? And here's an interesting fact which I won't prove. It's often, not always, proven in courses in information theory, that the Shannon capacity, like the maximum throughput possible, is identical, at least for stochastic channels, under all of these model perturbations, right? This definition is really very robust, right? You cannot really talk more reliably, regardless of how you measure your success criterion and so on. Okay? Very robust definition. Okay, but not quite so robust in the ABC setting. Okay, so this is the stochastic binary erasure channel, and you've seen this before. I'm pretty sure you have, right? You have x's are zeros and ones. With probability p, a bit gets erased. With probability 1 minus p, it stays as it is, right? And you want to communicate reliably over this erasure channel. So you can specialize the more general notation to this particular channel, and the capacity, as I'm pretty sure many of you have seen in information theory class, for a binary erasure channel is 1 minus p. And here I'm going to go super quick on this mostly because we'll revisit this for later things. But again, I'm pretty sure you've seen things before, right? So you have you want to transmit a binary message vector m over such a channel, and one common strategy is to use the linear code. So this message has some nr bits. You choose a generator matrix which is n by nr. This is like randomly chosen, let's say Bernoulli half, for example. So you choose a random such thing, and this is random code. In this case, the random code is the ensemble of all possible roughly 2 to the order n square possible matrices that you could choose over here, right? A truly random code, not a random linear code, would be a much larger ensemble. This is a smaller ensemble, but anyway. Now, how do you prove that this is a good ensemble? So there's usually two things you want to control. Firstly, you want to control the probability that the random noise vector is too heavy or too light, right? But mostly too heavy. So the probability that the Hamming weight, the probability that the number of ones in the transmitted vector is too heavy, has too many ones in it, that's pretty small. Right? So this is just a standard concentration inequality. This is basically saying if you flip a bit with a probability of being 1 with, if you toss a coin and the probability that the coin is heads is p, you toss it n times, the probability that's not too close to np is exponentially small, right? You can prove it by the Chernoff bound, you can prove it by Asano's theorem, multiple different ways, lots of effort in getting the constants right and so on, but none of that will really matter here. So the noise is sort of typical. It's not too heavy, it's not too light, right? And then the remaining argument is sort of combinatorial a little bit. It basically says if you have a random m by n random matrix, then the probability that this random m by n matrix is not full rank, if you just look at the rank over the binary feed, the probability that's not full rank is just a product of something like this. And you can approximate it as basically as 1 minus something close to exponentially small. I mean, basically exponentially small, right? And the argument again is fairly standard in coding theory. Basically, I'm not going to go through the details carefully. Yeah, I really do want to stop quickly, but like after I get to a certain point. But basically, it's like saying, well, the first column should not be all zeros, right? So at least the first column is good. Now, if the first column is not all zeros, well, the second column should not be a multiple of the first column, right? It should not be identical. The third column should not be a linear combination of the first two, and so on. And then just do some calculation, you'll get there, right? Okay, so now the noise vector is not too heavy, and the matrix is full rank. So then, decoding is sort of clear, right? So what that says is, well, you hopefully get close to n minus np unerased locations, and this submatrix is going to be full rank, so you can decode, right? And therefore you can decode and blah blah blah. Now, and since this is just linear algebra, it's not even very high complexity. It's like order n cube. Even if you do it naively, you can do it faster, and all of that. Oh, by the way, converses are often in information theory proved via Farmer's inequality. There's also a very nice converse proof in Ron Roth's book on coding theory. It's a slightly different geometric argument, which is also worth knowing, more useful in some techniques, in some contexts, but there are converses. So you really can't do better than 1 minus p, okay? And as I just said, you can, the computational complexity is not heavy. It's like order n cube if you do Gaussian elimination. Now you can do more clever things. It doesn't have to be a Bernoulli half matrix. It turns out there's a nice little paper which says, I mean, not in the context of coding theory, but basically a nice fact to know that if you choose a Bernoulli P matrix, where P doesn't even have to be a constant, it could be something like basically log n over n, even then this fact is basically true. Okay, so it could be a very sparse matrix, and even then it's going to be close to invertible. A very sparse or a very dense matrix, both of these settings, it's true. And then in these settings, you can do linear algebra a lot more quickly. And then there are even more careful ensembles you can choose, these LT code, fountain codes, blah, 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 where it's even quicker. There are all these other trade-offs, right? People have spent a lot of time talking about, which I will not talk about. But I just want to point out, look, a lot of cleverness has gone into making sure that we have good codes, not just in the capacity achieving sense, but also in the computational sense and so on, right? And these are close to the Shannon limit. You can also analyze this particular code construction, show that it's even not too bad in the second order sense, right? You're like order square root of n bits away from the capacity and all of that. So, it's a nice example. Like even just this basic example of a random linear code for the binary erasure channel already exhibits many of the sort of subtleties that you would want to teach, maybe even in a second course in information theory, right? And this is one of the reasons why Rudy likes to say, well, whatever we learned about the coding theory, we first learned from the erasure channel, right? So that's a good thing. Now, what we'll begin to see after the break will be what starts breaking down in the context of adversarial jamming channels. And we'll start with a classical Hamming channel where the adversary gets to choose the noise. What will break down will be, in some sense, the really simple fact that we used implicitly in our assumption here, that this matrix is random. Okay? So even if the full matrix that you choose is random, now once the adversary gets to see the gets to choose which locations to erase, he can subsample from the matrix so that the subsampled matrix has some certain correlations within it, right? And this simple little fact will mean that you cannot hope for a rate of 1 minus p anymore. You can only hope for a substantially lower rate, and we'll see some converse arguments and so on. Okay. All right. So time for a break. So it's an art. But first, any questions if you have any? Yes. Loudly, please. In fact, almost none of the codes I'll be looking at will be linear codes. This first example was just to present a specific concrete example. But yeah, almost all are achievabilities. Not all. In some specific cases, we know linear codes work. But there are strong reasons why linear codes actually behave terribly against adversaries. Okay? And we'll, if I remember, I'll highlight that later again. If I don't, let me just say it now, just while I remember. So the point of a linear code is that, as you may have studied, the nearest code word to every code word is always in the same direction, right? You may have studied this in your coding theory class, like the minimum distance code word, you can always add to any other code word and get another code word, right? So what that says is that for a linear code, if an adversary wants to jam you, he'll always push in the same direction. He doesn't even need to know what is being transmitted, right? So linear codes for this reason are actually quite bad for adversarial channels. Okay, not all adversarial channels, but many adversarial channels, and that's why we'll have to use at least slightly nonlinear codes. Okay. Any other questions?